All right, so this is going to be a lecture on musical sound, and musical sound is slightly different than just regular sound, and I used to have a chalkboard in my classroom, and I'd love to scratch my nails on the chalkboard and torture my students, which I don't have anymore and I can't do it, to demonstrate the difference though. Not all sound is considered musical. It has to have certain qualities about it. Okay. There are a couple classes of musical instruments, and this is just a broad range of the classes of musical instruments. You have strings, woodwinds, brasses, percussion, and keyboards. We're going to look at the qualities of some of these. All right, musical notes. What's going to make things music versus noise? All right, let's look at these qualities. One is going to be duration, how long something lasts. Two is loudness, and that's going to be the amplitude, the amount of, air that is being compressed, the amplitude of the wave. Pitch is going to be the frequency, and then there's something called timbre or quality, and that is going to be sort of these overtones, which we'll get to in a few slides here, that different instruments play. Okay. Duration, pretty simple. How long? From the beginning to the end of the note. Loudness, again, pretty simple. That's the amplitude, how much air is being compressed. The loudness of a note is indicated by the amplitude of the sound. Okay, pitch and frequency. The faster the vibration, it's going to have a shorter wavelength and a shorter period. The faster the vibration is the higher the pitch that we hear, okay? So something that is really, way up here and high has a short wavelength and a very fast vibration. Pythagoras. Yes, he likes ratios. He likes all kinds of ratios, not only the Pythagorean theorem, but he liked music and the ratios in music. And he discovered that different musical notes were related by mathematical ratios. Guy really likes his ratios. And certain things could contribute to those ratios, like the length or the size of a musical instrument could contribute. You can see this even in the picture here. You can see like filling up with a cup with different amounts of water will make different sounds. Okay, so as we look at different ratios, let's look at octaves. When you have what's called an octave, it is a note, and it would be produced, if you're looking at strings, by two strings, and one would be half the length. There's a nice ratio, right? Half the length. And these have a similar sound to us. And in Western music, we like the sound of these octaves played together. I guess men and women typically sing an octave apart. And so octaves are going to be, frequencies will double as we look at octaves, and wavelengths will go to half. So another ratio is what is called the perfect fifth, and this is if the second string is 2/3 the length of the first string. All right, and these would be like the difference of the separation between tenor and a bass, or a soprano and an alto. Okay, now we have what's called the fundamental and then overtones. And a fundamental frequency is the lowest frequency. It's that can be created by a standing wave. All right, so remember that really boring one we did with the slinky? That's kind of like the first harmonic. That's the fundamental harmonic. And then overtones are going to have to be twice, or 3 times the fundamental frequency. You can't really get like a one and a little, right? To get that wave. I remember you guys playing with the frequencies. You can't get it to do like weird things. To get a standing wave, it's either got to be, one frequency, or double the frequency, or triple the frequency. All right, so between one octave and the next octave, you have 12 steps. And when you get to that second octave, you're going to double the frequency. So for example, the frequency of concert A, which is just the A note right above middle C, is 440. If you were to go up to the next A, you would get to 880. And as you look at the notes in between, you're going to find that there's this mathematical formula that will tell you the number of steps. And so you can see in the formula the frequency equals 2 and then exponent the number of steps over 12 times the original 440. So if you had 12 steps, you would be all the way up to that next octave. It would be frequency equals 2 and then exponent 12 over 12. So it's going to be just 2 times 440. All right, and then everything in between is going to be those middle notes. All right, so here is an example of all these middle notes, right? And don't worry too much about this math. We're not going to do this math. I'm just showing it to you. You do need to be able to get this chart down because we're going to use this information in a lab. So I do want you to have the chart down, but we're not going to do these middle frequency math. I will give you the notes anytime I want. I'll give you the frequency for the notes. But here you go. Here are the frequency for the notes. Go ahead and write them down. All right, here's a visual of what the piano keys look like. Remember I said that if you're, really high, way up here pitch, those are very, very fast frequencies with very short wavelengths. And here you can see the harmonics of the C's. So the first fundamental C, and then you have the next harmonic, and then you have these harmonics going up. As you look going up, and each one is going to be a doubling or tripling of the wavelength. All right, string instruments. It's a standing wave, just like we created with our slinkies. Standing wave, vibrating strings causes the forced oscillation of the sounding board. All right, and so the frequency is going to depend on the length of the string. And so people will put their, fingers on it and shorten the string to get different frequencies. It'll depend on the thickness and the composition. So there's several different, obviously, strings there. They'll have different thicknesses. And then there's the tension of this string. And all of those contribute to the frequency. All right, now that you have the loudness, that's going to depend on the amplitude of the oscillation, the mass of the string, and the frequency. Yeah, this is just kind of cool evolution of the piano. There you go. All right, musical pipe instruments. These are going to be ones where you're going to blow through and create a wave inside the pipe. Okay, so here's a very simple diagram of that. You're going to create a standing wave just inside the pipe. And the way you're going to do that, blow on the mouthpiece. All right, so you have the brass and the woodwind vibrations. So vibrating one's lips, like on the trumpet, these are different ways to create vibrations. Okay, blowing past an opening is a flute. You blow on top of it, you'll create a vibration. And blowing on a reed, vibrating a reed, that also creates a vibration. Okay, we're going to actually do a slightly different version of this, but you can take a straw and cut it and blow on it, and depending on the length of that straw, you will get different notes. We're going to do a different version, but you can do this. Okay. For natural horns, you're limited to the harmonic series, the fundamental frequency, and then the overtones. Okay, and the reason is you're not varying the length of these. If you want to do any of the other things, you need to vary the length. Okay, so how are we going to vary the length? There's different ways of doing it. And we'll look at a few different ways of doing it. You can do finger holes. There's different ways to vary the length. Right. For a trombone, you can do a continuous slide, so you can get everything in the middle. It's a continuous slide. Obviously, that gives you some versatility. there are valves that you can use for the trumpet or the tuba and the French horn. All use a valve system, and that will vary the length. Okay. So let's look at woodwind instruments. These are, we're going to create standing waves, and now you have finger holes. So if you look at this top instrument here, let's see if we can get this top instrument here. So all these holes are supposed to be filled up, right? So the air is not coming out of them. And here is your complete wave. If you open down here, you open the last two holes, you now have a shorter wave. This would be a higher frequency. If you open the last four holes, you just cover the first three. You're going to get an even shorter wave and an even higher frequency. Percussion instruments basically are just going to be, we are going to strike something, we're going to whack it and create an oscillation. We're going to hit something. Kind of fun. Drums, you know, all of these, the xylophone, all of these are percussion instruments. Okay. So the drum heads are just stretched membranes. They're going to vibrate up and down. And that's going to vibrate the air. Very simple. And yeah, these are obviously vibrating slower than real life, but you know, gives you a visual for it. Okay, timbre or quality. Remember we said timbre or quality, we're going to talk about it later. So a musical instrument playing a single note produces not just the note's frequency, but others as well. And mostly they're going to be overtones. A tuning fork, if you're to play a tuning fork, the whole point of a tuning fork is to tune something, right? It's not to be beautiful. A tuning fork will play just the fundamental frequency. It's listed on it. It's going to play whatever, 440 hertz. But a musical instrument is going to play something much more beautiful. How is it going to do that? It will play that fundamental frequency, but it will also play these overtones, and the number and the amplitude and the quality of these overtones, the numbers and the decibels and all that fun stuff is going to be specific to each instrument. All right, so as we look at different instruments, we have at the top here a guitar. You can see there are a ton of overtones being played for one note. All right, and that's what gives the guitar its special quality. Okay. When we add different frequencies, the waves are actually going to add together constructively and destructively, just like in the previous notes. We talk about constructive and destructive interference. And as they alternate, between being in phase and out of phase, you get this pattern and a comb. This is two combs on top of each other here. And a comb oddly shows this very well, this visual from a cone. But you can see you have this pattern of, you know, oscillation here of an area of like dark comb here and then light comb here in between. That's what happens with sound waves, and it creates something called beats. And you can hear these beats, and hopefully we'll be able to do the demo in class where you can really hear the beats. But if you play two notes that are similar but not identical, you'll almost get a wah 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 sound. And you can tune instruments by taking a tuning fork and playing the note on the instrument. And if you hear the wah 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 sound, they are not perfectly in tune, because if they're perfectly in tune, you're not going to get these beats. You're not going to get these areas of constructive and destructive interference like that. All right, so this is like an example of the beats, all right? And you have two slightly different wave frequencies here, wave A and wave B. And when you play those together, you get this area of increased amplitude here, and then less here, and then increase, and then less. And that's what sounds kind of like a wah, 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 that beat. And if they were perfectly in tune, you would not get that. Okay. What is dissonance in the ear? Remember I said not all sound is music. There's lots of things in life that aren't music. And And so one thing that we don't like are when two notes are close together. We find that very unpleasant. So it's like almost better to be way off the mark than to be going for something and being slightly off. We find that very, very unpleasant and dissonant.